professor of statistics at Stanford, and has worked on many different interesting applications of statistics and data. Today's talk is about problems in manifold sampling for data science applications.
Susan, can you hear us? Susan, how about now? Can you hear us?
Can you hear us, Susan?
Okay, I took off the headphones. I still can't. Can you say something?
Can you hear us now? Hello, can you hear us now?
Yes, I can.
Okay, great. We'll start again. Our last speaker today is Susan Holmes, professor of statistics at Stanford. Over her career, she's worked with data from many different domains, using statistics and data science in many different forms. And today's talk is about manifold sampling for data science applications.
Okay, thank you. Sorry about the technical, and I hope you can hear me and let me know if you can't. I'm happy to be an outsider and talk to you about why we care about all the wonderful ways that you have devised to do sampling. And I'm going to talk a little bit about what we do in statistics and applied work. There's a paper about some of this work, which has already appeared 10 years ago with Mehrdad Shashahani and Percy Diaconis, which is called Sampling on a Manifold. And there's other work about the manifold learning, which is work with a PhD student, Len Nguyen, that I'll also talk about. Our motivations for wanting to sample from manifolds come from topological data analysis and their verification using generative models. And we use sampling also for goodness of fit and something which is called Neyman smooth test, which involves sampling from manifolds from non-uniform distributions. I'm particularly interested in the field of biology. We use a lot of methods for doing manifold learning, and that brought up several problems that we have. In particular, there are open problems in identifiability that I'd like to have time to talk about at the end. So first of all, the first part is about how do we go from discrete data to trying to infer actually an underlying continuous topological support. And the typical example is that of the method developed both at Duke and at Stanford by topologists, computational topologists, to use estimates of Betti numbers. And this is done, for instance, you have points random say uniformly on a torus, and then you blow up those points a little bit, and we construct what's called persistence diagrams. And from the persistence diagram, you can infer what the Betti number of the shape from which you were sampling is. So in that protocol, the way we go from the discrete points is that we make little balls of radius epsilon around them, and then as they connect up, we have numbers of connected components which are different, and you can compute what the number of holes and the way in which the simplices are assembled. And in order to verify this, we were doing work with Gunnar Carlson at Stanford at the time. The first thing they wanted to do was take a torus and generate a random points on a manifold. So you take finite samples of points on the manifold that you want to try and find the shape of, and you use some kind of computational topology tool to compute the persistence diagrams. And then you evaluate the error rate. That is, you've computed the Betti numbers and you want to know how much you're off. So the first thing that they did was to say, okay, here's the equation as we see it in some sense of the torus. And we're going to take those equations and say we generate a random between 0 and 2 pi theta and psi. And then we're going to embed that in 3D. And if we do this, we get points like this when they're projected down. This is what the projections look like. No, it's sort of supposed to be like sesame seeds on a bagel. And you hope that they're uniformly distributed on the manifold. As it turns out, in fact, and you'll notice this, this naive method over samples or creates too many points when there's high curvature. And so that's a problem. And this naive wrong method uses the embedding and writes down, in some sense, the area measure. But you take the surface and you thicken it by, say, epsilon, so you get something which is 3-dimensional, and then you compute, the usual volume, and that's why they use the standard embedding of the torus. So this area measure is normalized in some sense in the wrong way to give the uniform distribution, and it's counterintuitive. So many mathematicians, when they're trying to generate uniform data on a manifold, they get it wrong. And so the sample points not being uniform, we came back to that and studied it and tried to say, what is the way in which you're going to make a transformation so that you get actually the uniform measure on your manifold? So you want to calibrate your algorithms, but since you want the uniform distribution, you first have to generate uniformly. We also do this in statistics for goodness of fit tests. And so Fisher had a procedure in which you define a goodness of fit where you take the observed data and you have sufficient statistics from that data, and you're going to compute many different instances of points generated on a manifold with that given sufficient statistic. And in particular, it might be a gamma distribution or something from an exponential family. And we want to find out whether your statistic on the observed data is typical given the sufficient statistic. So testing for the gamma distribution, the sufficient statistic is the sum and the product of the x's of the observations. And this is a compact n-2 dimensional submanifold in Rn. And we want to sample from M, and we want to test random variables independently drawn from a gamma density with given S and P. So again, this is a case where we want to sample from manifold, but in this case, we don't want to sample uniformly from it. We have a gamma density. So the conditional distribution is what we're interested in, and it has a simple density with respect to our area measure. And this is sort of typical bread and butter statistical goodness of fit test that one would want to do, but it also applies to constraints in physics and chemistry problems. In computational chemistry, for instance, you have configurations with given interatomic distances, and certain angles are fixed as well. And then you want to generate all samples which verify those conditions. And so that's, again, sampling from a manifold with given constraints, and it might not necessarily that you want to do uniformly. So we're going to study generalizations, and the way we go about it is we are going to embed the M, the submanifold, in Rn, and we have a density Rf, and we're going to look at, mostly we'll use Hausdorff, we'll use the M-dimensional area measure on M, and we draw samples from a normalized version of F so that it's a probability distribution. The only other place where we've found good literature on this was an old book by Chur, and it's a different development in that we're using embeddings, and he went directly with Riemannian manifolds and smooth functions. So it's slightly different development. So the tools we use come from geometric measure theory, and in all of our applications, what we're interested in are pieces of manifolds. In general, they often have corners for reasons of constraints which occur given in this case, given the sufficient statistics. So this is the type of manifold that one might get. And then we'll be using, well, Lipschitz functions are very important, and we'll suppose that the sets we're interested in are M rectifiable. That makes everything work properly. And we'll be considering that lambda n is our Lebesgue measure, and we define, and we use all the time, the Hausdorff measure as it's defined on the rectifiable sets and that have coverings. And so this is sort of standard in geometric measure theory. The constant that you see, the number, here we have alpha m, and that's the volume of the unit ball that comes in. So for closed sets, that Federer shows that you can write this, what I said at the beginning, the way we define the area measure as the limit when epsilon goes small, it becomes small. That is, you fatten by epsilon and then you make it decrease in size of the Lebesgue measure. So that's the justification in some sense of the heuristic that we had at the beginning. And that's usually how people think about computing area measure on a manifold. One of the most important components, and in some sense it's a generalization of the change of variables, is that we're going to use the Jacobian for computing the area measure. And this is just the standard Jacobian. That is, if you have a function which is differentiable from Rm into Rn, and you define the linear map of differentiation, this limit here, and the Lipschitz function, a Lipschitz function is going to be differentiable almost everywhere with regards to lambda m, the Lebesgue. And for that, we have also the matrix, which is given by the partial derivatives, which is the usual notation that we have, the DIFJ. So that's the differentiation. And the k-dimensional Jacobian is the maximum k-dimensional volume of the image under df of x. And in general, it's defined with regards to the norm of a df of x, depending on what the rank is. And of course, if the rank if it's degenerate, then this is 0. But in general, it's the absolute value of the determinant of df of x. Now, the area formula uses that, and we have this transformation of measures, like a change of variables. And we can write that the integral with regards to of g of f of x is equal to g of y. And here we just have the number of times that f of x is given to a given value. And if the function is 1-to-1, this disappears, and that will just have g of y and Hausdorff measure on the right. So this is a standard in geometric measure theory, but it's actually the basis of what we do when we do the algorithms for generating uniform according to the right measure. So the example of the curved torus, let's come back to the example that was wrong and see what was missing. Well, it was the change of variable formula, which is necessary. And so here we have the determinant and we have this extra element, r squares, and then capital R plus little r cosine theta squared. And so that is going to come into the algorithm when we change the measure. So that's why, in some sense, close to in the middle of the circle, there are too many points because there wasn't the right weighting. When we have the example of the gamma distribution, we've given sum and product. These constraints, again, can be written out. We can decide to take a function where we're going to fix the first two coordinates, and then the other coordinates, everything will be dependent on the sum and the product. And so we can write out that if the sum of all the values except the first two is s, and it's s minus t, and the product is p, we can write out that the x1 and x2 have to be of this form. And we can parameterize m in two different ways, depending on how we constrain the order of x1 and x2. But let's say we look at m plus. And we can define U, this as our manifold with the conditions. And we have the change of variables that we can write out. So F1 and F2 are our functions. And then we can write out what the differential is and what the Jacobian will be. And the Jacobian can be written out quite simply in this case, because we're left with just a 2x2 matrix to write. So the density of the m-2 dimensional area is actually computable, and we can do it just taking this determinant of the Jacobian. So these are not using randomness right now. They're using formulas to change of measure to take into account the constraints and the fact that we're sitting on a manifold. And those are sort of, caveats about it with the measure 0. Now we can use the we want to do the conditional distribution on the manifold with a gamma distribution. And for that, we can use the co-area formula, which is stronger than the area formula, which allows us to compute the conditional distribution. And this gives us a way of solving, in some sense, Fisher's test. And so we have a definition. I won't go into too many of the details, but this is the main proposition, and the proof is in the paper. But we have both the marginal density, and we can write out, in some sense, what our conditional distribution is going to be and compute it from our differential from the Jacobian. Now, once we've written that out, we actually have to do a little bit of simulation. So in the case of the curved torus, I told you we have a change, we have a density, we have this change from the uniform, we have to add this extra term in, and we can use a random number generator. In this case, it's very simple. We don't even need MCMC. And if we write out the formula, we can do rejection sampling because we have exactly the area under the curve. And this is what the rejection sampling proportional to this value, this is what it gives you. And the result of the points, this is the torus, it has quite a large, quite a small hole in this case, but this is different projections of the points from the 3D. And what you see is these are all uniform, and you don't have this buildup along area, the places where there's high curvature. In the case of the sum and product, we have to do sampling from the area measure, and we do have this change, a variable, but we have to actually do some Once we have the formula with the constraints, we do Gibbs sampling, but we have to keep a certain number of the coordinates fixed. We can't just fix 2 at a time, but we can use a modification of Gibbs sampling that works in this case. So if you wanted to naively say, I want to sample on a manifold with a Markov chain, and we've seen this in a couple of papers, there is an intuitive method for doing it wrong, which is that if you have the manifold and it's, compact embedded manifold, and you want to sample from the area measure, you might say, okay, I'm going to take a neighborhood of my point and I'll restrict myself to that neighborhood, and you'll sample from the area measure restricted to that. And you could pick a point in your neighborhood restricted to that measure. And in fact, although locally you're using the right area measure, globally, this doesn't give you the right answer. And maybe the best way of seeing that is to think about it not on a manifold, but think about the equivalent problem, but on a graph. And so suppose that you have the discrete case and you have a finite connected graph with a probability measure. And here we want a probability measure which isn't uniform, so it's pi of x isn't uniform. And at each point we have a neighborhood, and we'll suppose that if x is in the neighborhood of y, y will be in the neighborhood of x. And for instance, you could have a graph distance fixed for your neighborhood, say a ball of radius r in graph distance, and you take the Markov chains such that you choose y in your neighborhood, so at a distance of say 2, and with a probability pi restricted to that neighborhood. So here, this is the kernel would be, I go from x to y with probability pi over y over pi of the neighborhood of the measure. And this chain is reversible, and its reversing measure is pi of n of x over z. So at point x, we have this as our measure, and it's not equal to pi unless pi of nx is a constant. So we don't get pi as our stationary distribution using this. And so that is not, that wasn't the goal. So you see that there's a problem when you take into account just locally your conditioning. It will depend if you have very different neighborhood sizes, then you'll get the wrong measure. So this was done, and this people have analyzed this method of creating a chain, and in the case of compact Riemannian manifolds in Lebeau and Michel, and they're actually, when they started off, they made that mistake. They weren't getting the right stationary distribution. If your manifold is just a curve, so and then you're just trying to generate on a curve, and you're using arc length for your area measure, this can be considered constant if your r, if the ball is small enough. And there's a theorem that we use a lot in statistics called the volumes of tubes formula, which enables you to say that the volumes are going to stay constant. And so, but this won't be true if you have a higher dimensional manifold, so not for just the arc length, but if you're in higher dimensional manifold and you don't have a constant curvature, for instance, Gaussian curvature. So in general, it's the curvature which is going to pose the problem. And we'll see later on that curvature poses also problems when we want to go back to manifolds from data. So curvature is the problem. Maybe I won't take, since this is a shorter talk, I won't take the time right now to go through, it's in the paper, but we did other types of tests. Name and smooth tests are a good example of using it's trying to use the inverse CDF to bring things back to uniform, but with a specific exponential family. It's quite a nice test, and it gives rise to another set of manifolds, but I don't have really the time to go through the details of that. So I won't do that, but I want to talk about manifold learning and the open problems. So I just talked to you about cases where we had manifolds which were given to us, and either we were doing generative models or we were trying to do testing, but we had the equations of the manifold. Now, what often happens for me is that I have data which are very high dimensional biological data, and we try to learn if there's an underlying lower dimensional manifold, which could explain some of the variability in the data. In particular, we look for things like landscapes, fitness landscapes, or energy landscapes. And we're trying to learn a natural parameterization in that case. This occurs in very simple cases. So with Percy Diakonis and Sharad Goel, we looked at high dimensional voting data, political science. And in that type of data, we got two horseshoes. If you use kernel multidimensional scaling or a kind of local manifold learning method, you get very clear arcs, two arcs. The reason our analysis worked so well in this case, and we were able to do it actually all the way through to the spectral analysis, was that the sampling along the two manifolds here was practically uniform. So we had uniform sampling along the manifolds. In general, that doesn't happen. So in the type of data that I analyze, I do the microbiome. And in this case, these are samples that are taken from the ocean at different depths. And the gray points are actually the data points as they lie in two-dimensional dimension reduction factors. And these are the projections. And so they're the projections along a one-dimensional manifold, which is, in this case, a gradient. And we were able to understand this gradient because it was the depth at which the samples were taken. And so here we have the depths. And so this is the deepest and this is the shallowest, the samples. And of course, the depth explained the composition in terms of bacteria because the depth influences the amount of oxygen and the amount of light that the bacteria have. So it's very easy to explain. And what we saw was that the uncertainty with which we know parts of the manifold are very unequal. And so you have parts of the manifold which seem rather empty. And so you have non-uniform points along the manifold, and this poses problems both of uncertainty quantification, but also of being sure actually that this was enough information to infer the manifold form. So unfortunately, real data do not sit uniformly distributed on a manifold. So when we're trying to do manifold learning, we want to do transformations so that we have changed the metric to account for the difference in distributions. And this, I'm not going to give you all the details of how we did this, but this work that we did with LAN involved making an inverse variance stabilizing transformation locally. So we make the data, first of all, homoscedastic, which is already one step towards being uniform, and then at least more uniform. And this is done by changing the metric. So you can change the metric so that points which look as if they're denser are spread out by spreading out. If you imagine that the manifold is elastic, you spread out the manifold that way. And so you want to use a Riemannian metric on the manifold, which is locally different and which takes into account the variance. So the best data for manifold learning are uniform, and we have transformations of the data where we try to make the data more uniform. And while when we know the dimension of the underlying manifold, so in the case of the gradient for the Tara ocean data, we had a good reason to believe that the dimension, that it was one-dimensional manifold, that it was a curve, a gradient. But when you don't have the underlying dimension, then it becomes much more difficult. There's an identifiability problem which remains, which I think is an interesting open problem, which to my mind, some of the people who do optimal transport would be able to solve. And I'd like to say that problem, and maybe you can ask questions about it, but I'll explain it to you a little bit intuitively. It's a geometric problem. That is that if you're not told what the manifold is or what even the dimension of the manifold is, and that you know that your data are very non-uniform, that is, they also have clusters, when you start doing manifold learning, many of the algorithms, the first step that they do is say, I start off with 20,000 gene expressions, so I have 20,000 features. The first move that is made is to do a principal component analysis or dimension reduction, say down to 20 dimensions, to reduce the noise. And in those 20 dimensions, then people do t-SNE or UMAP or methods that are considered to be manifold learning. But in that first projecting down the data, there's a lot of clumping of the data which appears. So if you looked in, say, the projection in the first 2 dimensions, you might see something like this. And what this is supposed to represent, the scale, the light shows much higher density points. And so you have clusters, you might have clusters of points which seem to occur in these areas. And the question that comes up, and this might, be explained by, if it was simple, this type of configuration of points. And these clustering here, you have clusters of points which are lighter, and you see that. But in fact, if in your original data, the data weren't linear, but they're lying close to a very high dimensional manifold, we would see them say that instead of being clustered, the points lied on a grid, or practically on a grid, uniformly distributed on a manifold, and that they were projected down. Then you would see the same thing. And so we don't know whether the clustering here is due to the fact that there are actually big changes in the density, or that there are big changes in the curvature. So the way about that has been for us to try to even things out, to make things more uniform, but that's been very difficult to wrap our heads around. And there's a very interesting sort of theoretical computer science problem about the identifiability of the change of density and the change of curvature. And as I showed you, the curvature changes the way you get the uniform distribution, and you have to take it into account using the Jacobian, but that comes into machine learning as well. Okay, so I said the problem that I'm interested in, asking you in some sense, and for the references, the main reference that we, used is the paper with Mehrdad Shashahani, which appeared, and there are other papers here by Gunnar Carlson on doing TDA, and the book that we used is Federer's Geometric Measure Theory. So thank you for inviting me.
Thank you. We have time for questions.
Are there any questions? I took down the...
Yes, can you hear me?
Yes, I can.
Sure. So I know a couple of things about optimal transport. And just thinking about your open problem, my understanding of the optimal transport literature is that rather than solving your problem, it somehow dissolves it. So
Okay.
in the sense that in the literature on curvature dimension bounds in optimal transport, there is actually no clear distinguishing between the curvature and the density. So what is done is that rather than working with a manifold, you work with a manifold with a stipulated reference measure. And then you define a new curvature tensor, which has the reference measure somehow embedded in it. So this thing is called the Bakri-Emery curvature tensor. And then all of the curvature data on the manifold is written with the not necessarily uniform reference measure somehow encoded inside the curvature data. So I have no idea how that would actually, whether that would be of any use to you, but somehow the problem of non-identifiability is recognized in the optimal transport literature, and they have just sort of accepted that this is how life is. So I don't know if that's informative, but you know.
No, I mean, I think it does solve the problem. For instance, in biology, there are things which you can never deconvolve. And so you just have to talk about them together. You know, the mutation rate and along a tree and the time and so there are some things which you'll never be able to identify. And I guess it does solve the problem, but from a practical viewpoint, in what we do, I guess I would hope that you could separate. So maybe that you could make transformations that take out some of the curvature. Yeah, I'm looking for ways of transforming the data, right? So so I get hold of the underlying manifold as if it were uniform. So an equivalent uniform is what I'm looking for. But that's good, although what you're telling me, and I know Dominique Bacry pretty well, and I know I can't read anything he writes. So it might be, there might be a more concrete place to read about that.
There are several theoretical computer scientists in the audience. Just to make sure we understand your last problem. So you have data that's coming from some unknown manifold, and you'd like
Yes.
to, you don't know its curvature. You may know nothing about the manifold. You see a projection, and
Yes.
it looks dense in some places, but that could be, so do you really have no assumptions on the manifold at all?
Well, no, usually, no, that's not fair. Usually you believe it's quite low dimensional. So it might be that you believe that it's 2 or 3 dimensions, but you don't know whether it's 2 or 3 or 4, but it's quite low dimensional. But one thing you are sure is that your data are not uniformly distributed on that manifold.
I see. But what about some kind of symmetry or property of the curvature itself? So do you know, for example, if it's okay? I see.
No, usually that part is just all the data. I mean, sometimes the best we can do is like what we do in what's called response surface design, is to say, we know this is more highly curved. We need more data. You always need more data where it's more highly curved. And so, it tells you that you need more data in the places which are highly curved, in some sense, so that you can spread out.
So can you ask for more data in specific places? Do you get to go back and ask?
That's what I do, yes. Yes, that's what we do, because you usually can't answer the question in one go, right? You have to generate a hypothesis and then go back and test it, right? But yeah.
Hi, thank you very much for a great talk. I'm just wondering, it's probably a very naive question, but have you thought about sampling from a manifold with non-uniform distributions? And And under what circumstances would you call the distribution unimodal?
Oh, so we don't know. I mean, unimodal means, just that there's one maximum in the density. It would mean, for instance, that you wouldn't have clustering, that you believe that it comes from a homogeneous population. But in general, when you're sampling from a manifold, you never know that they're, it's very non-uniform, the sampling procedure, but it's hidden to you. So there are very strong biases to parts of the manifold. But that part, you don't know until sort of the second or third time around. As I say, we collect more data and then we go back. But it's definitely one of the big challenges that we never can suppose uniformity. And well, unimodality, it's not, for high dimensions, it's usually clustered in different ways. So it doesn't have just one clean population. It's mixtures. So in some sense, we have mixtures. So.
Just a clarification question about the identifiability issue. So it seems like if you project to a linear subspace, like what can be confused with density is actually like if, for example, if you take a one-dimensional curve, if the curve has a large angle with a linear subspace, for example, it's near orthogonal, then it projects as if it was large density, so that you cannot distinguish. But it seems like this is like a first order derivative, but curvature is like a second order derivative.
Yeah.
So that's the question you are talking about. It's actually about the large angle stuff.
Yes.
Okay.
Yes.
Thank you.
And I try to illustrate what goes on just by doing the torus to show how the curvature modifies, in some sense, the density that you get naturally. I don't know whether that was so helpful, but it's definitely the case that that's our intuition. And of course, all we can do is negative experiments where we show that we can identify. That is, you can generate data that look exactly the same by either taking a very curved surface and doing it on almost a grid, or you can just take a flat surface and then cluster the points. And you can get two indistinguishable distributions. And so I wondered whether, and I think you probably solved it by saying that the optimal transport people know that you can't do it. So then we have to do a step-by-step procedure for deconvolving. But
any more questions? Now let's thank Susan again.
Thank you for having me.
Meet you back here tomorrow at 9:30.